Hi everyone, in this video I'm going to work through a typical exam style question involving stationary points and the second derivative test. And if you want, go ahead and press pause and give this a try before watching the correction. That being said, I'll just move this question to the side, like so. Now we're given a function f of x which equals to x times ln of x, and we're told that x is greater than 0, and we're asked to do two things. The first, we need to find the coordinates of any stationary points, and secondly, we need to use the second derivative test to determine their nature. So let's go ahead. I'll write a little 1 here to say that I'm answering question 1. The function we're given is f of x, which equals to x times ln of x. And to find the coordinates of this function's stationary points, we need to equate its derivative to 0, and that'll give us the x coordinates. So the first thing we need to do here is figure out the derivative f dash of x. Now, looking at our function here, we can see that we're dealing with a product of two functions. Indeed, we have x, which I'll go ahead and call u, which is multiplying ln of x, which I'll go ahead and call v. Consequently, using the product rule, we can state that the derivative f dash of x is equal to u dash times v plus u times v dash. And so that's going to equal to u dash, which is the derivative of x, so that's just 1, times v, which is ln of x, plus u, which is just x, times v dash, which is the derivative of ln of x, which is 1 over x. And simplifying this, we can go ahead and state that f dash of x is equal to ln of x plus x times 1 over x, which is just 1. And that's the derivative. Now that we have that, to find the stationary points, we equate it to 0. In other words, we need to solve f dash of x equals to 0. And that's the same thing as solving ln of x plus 1 equals to 0. Which leads to ln of x equals to negative 1. And now, using the fact that the exponential e of x and ln of x are inverses of each other, we apply e of x to each side of this equation. In other words, we could go ahead and write e of ln of x equals to e of negative 1, and since e of ln of x is just equal to x, this leads to x equals to e to the negative 1, which is the same thing as 1 over e. And we now see that this function has one stationary point whose x-coordinate is 1 over e, but we still need the y-coordinate. And to find it, all we have to do is plug this value of x inside our function. Indeed, we can go ahead and state that the y-coordinate, so I'll just write y, is equal to f of e to the negative 1. And that's equal to e to the negative 1 times ln of e to the negative 1. That's equal to 1 over e times negative 1 times ln of e. Notice here that I've taken this power of negative 1 outside of the logarithm, and now we have an ln of e, and ln of e is equal to 1. So the y-coordinate is 1 over e times negative 1 times 1. So that's y equals to negative 1 over e. And we're done. We now have the stationary points x and y coordinates. And we could go ahead and state one stationary point, point, whose coordinates are 1 over e, negative 1 over e. And that's the first question answered. We move on to the second question. Here we need to use the second derivative test to determine the nature of the stationary point we just found. Well, for that, we need the second derivative. So if I start from the first derivative we had here, and in fact I'll copy that at the top here, the first derivative was f dash of x, which equals to ln of x plus 1. And so differentiating that again, we find f dash dash, the second derivative, and that's equal to the derivative of ln of x, which is 1 over x, plus the derivative of 1, which is just 0. So I won't bother writing that. And I'll go ahead and box this result. There we go. Now for the second derivative test, we evaluate this second derivative at the stationary point we just found. And for that, all we have to do is take the x-coordinate of the stationary point, so that's x equals to 1 over e, and place it inside the second derivative. So that would be f dash dash of 1 over e. And that's equal to 1 over 1 over e. and that's equal to e. Now, since e is positive, this tells us that at this stationary point, our function is concave up. And consequently, following the second derivative test, we can go ahead and state that the stationary point is a minimum. Minimum. There we go. And in fact, I'll go ahead and box that and connect it to the coordinates we had there. Done. And there we have it. We've answered the question. Now, although it wasn't asked, if we were to draw this function, it would look something like this. We'd have our x and y grid, like so, x and y, and the function starts just to the right of x equals 0, and it looks something like this. It decreases, it reaches the minimum, and shoots upwards. This point here is the minimum we just found, so it has coordinates 1 over e, negative 1 over e, and it crosses the x-axis when x equals to 1. Furthermore, this curve is concave up, as was suggested by the sign of the second derivative. And there we have it. That's it for this tutorial.